So what I'm saying is if you guys want to print out the notes and just take notes off of that, that's just fine. That would be my recommendation for this, right? You know, that way you don't have to copy down every single thing that's on the slides. Now, why do I recommend it that way? So we have 12 chapters of chemistry that I need to get through with you guys, right? And if I did my math correctly, I have you guys for about 39 classes this semester. Okay, so let's just make the math a little bit easy. Let's say 40 hours. Okay, so I got 40 hours to teach you guys 12 chapters of chemistry. That's really not a lot of time, is it? Right? So that's less than 2 days. So if we wanted to, we could sit here for the next 2 days and I'll just lecture straight, okay? And that would be all the time that I have with you guys for this semester, okay? So my point being what? A couple things here. We need to understand that as much as I would like to, okay? If I had to have more time with you guys, it'd be great because then we could, you know, slow down and, you know, work through things and make sure every question gets answered, all the problems get solved, these kind of things. I don't have the time to do that with you guys, right? Not at least here in lecture. You guys get the point that I'm saying with this, right? I'm going to do my best to give you guys all the information I can within the very limited time that I have with you guys. Now, this tends to be one of these challenges that come with general chemistry, right? So I could ask you guys, what positive things have you heard about general chemistry? You guys are snickering for some reason. And I could ask you what negative things you've heard of general chemistry. And nobody laughs. But it's all serious business, right? It's difficult. There's lots of math. It's a lead-out class. The professors are jerk. Whatever you want to say with it, right? And that's all true. I'm a jerk. Huge, okay? Huge. Thank you. One person laughed. The rest of us like, oh crap, right? No, right? And look, I'll be very honest, right? There is no such thing as a lead-out class, and of course that's the same thing as the, you know, the cops don't have quotas for tickets type thing, right? Everyone believes it, but they don't really believe it, right? Here's what I'm saying to you guys, okay? All of you in here have the ability to get an A in this class, I promise. It's not just me giving you guys a pep talk. I don't know any of you guys. Well, I know, you know, 1 or 2 of you stopped by my office, okay? But all of you guys can get an A in this class. Do you know how I know that? Thank you. Right? I know that because all of you guys showed up and you're wearing shirts and you're wearing pants. Okay? And that means you guys have rudimentary social skills. Remember that when you leave your door, pants are not optional. Okay? You understand this and you can work within that right mindset. What I'm telling you guys in a joking way is that you guys have all the skills you need. Okay? But if we're staying with the clothing theme here, do you guys remember learning how to tie your shoes? Do you understand it on the first day that you did it? I know I didn't. Can all of you guys tie your shoes now without even thinking? Most days, right? Some days, if it's early, right, still some struggles. Don't worry, Dr. H, I got Velcro. Bypass that, right? But I'm saying the difference just comes from practice with this. And that's where that's outside of the 40 hours that I had with you guys, okay? You're gonna have to start to practice this stuff so that you have the skills so that you can get an A in here, okay? Now, so lest you believe the gospel according to me, so to speak, right? What's the #1 predictor for how successful you're gonna be in general chemistry? There is a thing you can point towards and say, if you're good at this, you're gonna likely get a good grade in Gen Chem. Any thoughts? Begins with an M. Math. Okay? So now I sense the temperature in the room just went down a couple degrees. Like these cold shudders went through everyone. See, I didn't think I had to do math and chemistry, right? Well, remember, math is the universal language of science, right? It's kind of the foundation of everything. If you take a step up from there, you get to physics, right? And if you take a step up from physics, you get to chemistry, okay? So we kind of build upon those other things that are below us. We're going to talk a little bit about physics. We're going to talk a lot about chemistry, right? But all that stuff is built off of math. And so I'm expecting you guys to know some math, okay? Now, here's some good news. Okay? I don't expect you guys to know calculus. That's not part of this class. But just like calculus is really, 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 really important to know algebra, that's what we're going to be doing in here, okay? Rearranging equations, dividing, multiplying, getting rid of exponents, natural logs, all these kind of things, okay? So if you feel comfortable doing that, then you're going to be comfortable doing the math for this class. The math isn't really all that challenging. The challenge comes from, I'm going to ask you to apply the math from a conceptual chemistry standpoint, right? So I'm going to say, hey, I want you to calculate how many moles of carbon dioxide gets produced when we combust methane, okay? That's a pretty complex question, because I'm asking you to know what combustions are, right? To be able to balance the equation of combustion, to calculate moles and the math that goes along with that, right? So this is where the challenge comes from. There's a lot of layers that come into chemistry, okay? I could make an argument, you guys have seen Shrek, right? And talk about onions, right? Ogres have layers, onions have... Okay, thank you, all right. Same thing with chemistry here, all right? There's different layers that are gonna add the challenge to this class, okay? Now, you know what the good news is. You guys can practice this stuff, right? How many of you guys have the textbook? A couple of you guys, okay, good. Some of the other ones who didn't raise their hand, that means you guys, it's on order, right? Okay, good answer. Right? When I go to look for exam questions, guess where I'm going to look for them? In the textbook. You know why? I'm not very creative, okay? You know why else? How much money did you guys spend on this textbook? And the answer is, more than you wanted, maybe. Unless you had a friend who took this class before, right? And so, if you guys are going to invest your time and money into reading through the textbook and working those problems, I'm going to give you guys a reward for that, right? The reward is hopefully you guys get better grades on the exams because, hey, I've seen this problem before, I remember how to work through it, right? That kind of thing. Sound fair? Okay. What does that mean for you guys? You already know what's on the first exam, right? You know what's on the second exam? You know what's on the third exam, right? You know all these things, right? Because it's all stuff that's coming out of town. Sound good? All right. So let's see. We talked about the exams. We talked about the class. I scared you guys with math. Oh, labs, right? So lab is a part of this class, but it's with a separate syllabus and all that kind of stuff, right? Did you guys find that information already? It should be on Canvas there. Some of you guys have Dr. Freeze for lab, right? I think. What do you guys say? Who's teaching lab? I'm not sure. Right? Dr. Freeze, Dr. Tong is. Okay. And you guys are starting lab this week, right? So make sure you guys check your syllabus and the schedule for the lab there. Make sure you guys bring the appropriate material to the lab so you guys aren't, you know, dismissed from lab because you didn't have the appropriate attire and goggles and all this kind of stuff with that. Okay. Ask some questions beforehand. If you guys aren't sure what you need to bring, just drop Dr. Tong or Dr. Freeze an email there and they can get back to you on it. Okay. So I'm not involved in the Gen Chem side of lab things with you guys. So I'm going to be a little bit like, if you ask me a question, I'm going to be like, I don't know. So, okay. All right, let's see what else. I think that's kind of what I needed to chat with you guys about. Oh, so I'm going to be recording all the lectures. This is for the inevitability of somebody gets sick or just can't make it. In the modules part there of Canvas, there should be a link to the AMU YouTube page, right? And that's where I'm going to be posting all the lectures as I can, right? So take a look from there. There'll be a separate playlist for the Gen Chem fall 2021, and I'll be posting all the stuff there. So in case you guys do have to miss, just the lectures will be there. Somewhere there's a note taker in here. There she is, right? So this is also something that they're doing. I think they just sent an email. You can correct me if I'm wrong and spreading false information, please. Right? So, but my understanding is the notes are going to be accessible if you're absent because of illness. You'll just have to contact Adaptive Services. Have you heard about it? That's true? Okay, so there you go. So if in case you missed some notes or anything like this, just get in contact with Adaptive Service and we'll give you access to that also, right? So you have me on video recording, you're gonna have some access to notes. Tutoring's also available. I don't have the tutoring schedule yet, but they'll be emailing that out to everybody as soon as they kind of get that squared and settled in place. Yeah, what's up?
If you're bad at math, would you prefer to go to a math tutor or a chemistry tutor?
Yeah, that's a good question. Let me give you a bad answer, both. I guess the question is this, right? So, let me think about that a little bit. I'll give you an answer sometime in the middle of the lecture as it comes to me. But if I don't, then catch me after class. So let me think, that's a good question. Let me think about that one a little bit. like my answer on both still, though, just so you know. Right? Okay, so any other questions? And I think I covered what I wanted to chat with you guys about. Everything else, 100% good? I'm going to start talking unless you guys ask questions. All right, good. Let me start. So, chapter 1. Now, what I'm going to do here, or how we're going to walk through all these things, is I'm going to start from the basics, okay? So, what I mean with this is probably the first 2 chapters is not going to be all this much stuff that you guys haven't seen before, maybe in one of your high school chemistry classes, right? But if you're thinking back, you're like, hey, wait a minute, I can't even remember when I took chemistry in high school, or it was 4 years ago, or I didn't have that good of a teacher. Well, that's why we're starting here at the beginning, right? So I'm going to be walking through you guys with kind of the simple stuff, right? But here's the important thing to recognize. So I also teach the organic chemistry classes here. And so I had this same kind of talk with my organic students this morning, okay? By nature, chemistry builds upon itself, okay? So it means the stuff that we're going to talk about here in the first chapter, when we get to the end of Gen Chem 2, we're still going to be talking about this stuff, okay? We're going to go on into chapter 2, and we're going to deal with things like moles and calculations, all that kind of stuff. We're still going to be talking about that stuff at the end of Gen Chem 2. You guys get the point that I'm making here. This is another one of these stumbling blocks. What happens is, inevitably we hit chapter 3, and that's where things take a turn, okay? There's some difficult math that comes in chapter 3 there. And you're like, well, I didn't really understand all that well, but the exam's over. Oh, thank goodness, I don't have to see it ever again. This stuff's going to come back on every other exam that you guys see, okay? So why is it important to recognize this? Well, if you're having trouble now, and you don't do anything about it, what's going to happen? Trouble later. Got it? Do we want to wait until later? Yeah, sure, I don't want to deal with it now. I gotta forget that. Right? That's tomorrow's problem. You get the point I'm making with this? Don't do that, please. Okay? I'm always around in my office except for when I'm teaching in class. Right? Thursdays is when I teach labs, and then I have this class in the morning, 8 a.m. class that I teach. Other than that, I'm usually in my office. So if you guys have questions, guess what you can do? Just come see me, right? I think I put something down in the syllabus about office hours, right? I think there's some time on there. I don't even remember when they are. You know why? Because I'm in my office anyway. Just come on by, okay? If you can't make my office hours, just send an email. If you're just walking down the hallway and you want to know about strontium, just knock on my door and ask, right? And the worst I'll say is, can we come back, in 10 minutes or something like that, okay? So I'm here to help you guys out. That's what my job is. But despite all the years I've been a professor, I still can't read your guys' minds, okay? And so if you have a question and you're just sitting there in the chair and you're like, oh gosh, I know I'm the only one who doesn't understand this stuff, and I don't want to, be dumb. The person next to me might, judge me harshly. These kind of things that pop through our mind. Yeah, I saw that look there. That guy. Oh, okay. Well, you can move up here then, right there. Right. Right. But if you have, just ask the question, okay? I'm here to help you guys out. And look, if somebody makes fun of you, then I'll deal with that too, okay? So you guys signed up for this class, and it's my job to help you guys out, okay? I want you guys to get an A. In fact, I want all of you guys to get 100 on your exams. Do you know why? It's because I'm lazy. If you guys get hundreds, I don't have to grade in. Oh, okay, yeah, everyone got 100. This is easy, right? I get to go do whatever I want to, right? But when you guys start missing problems and I get grumpy, oh man, now I got to sit here and figure out partial credit and do all this kind of stuff, and then it takes forever, right? And you guys don't want me grumpy, right? Thank you. All right, also right, but just all I'm saying is I'm here to help you guys out. If you don't want to come talk to me, there's these videos on YouTube with links and all this kind of stuff that I put up there for you guys also. There's the tutoring, there's other professors, and Dr. Tom is teaching Gen Chem also, right? So if in case, for whatever reason you want to go talk to him, he'd be more than happy to help you. More than happy to help you also is what it is, okay? There's no reason not to get a question answered is what we're listening. Okay? Cool, all right. So let me try starting here for the third time now. All right, chapter 1. So really what we're going to talk about here is kind of some of these foundational things. I'm going to do a lot of, let's say, definitions, okay? So just for what it's worth, I very rarely, very, very rarely on exam say, what is the definition of matter, right? One of these things to start to get into the habit of especially as you're going through Gen Chem, but just out of curiosity, how many of you guys are going on through organic? Quite a few of you guys are? Okay. So, one of the challenges here then is we have to balance what needs to get memorized and what needs to be understood, okay? Memorizing a definition is not that hard, right? You just write it on a note card and every once in a while you stare at it and eventually it just gets lodged in your brain, right? That's just the way things work, okay? But understanding what something does and how to apply it, that's the challenging part of it, okay? And that's what I'm going to be pushing you guys towards. And for those of you guys who've read through my syllabus, you see the end part of the syllabus, we're talking about Bloom's taxonomy and all these kind of things there, right? The different levels of understanding. We're going to be moving towards some of those higher level understandings there, okay? So be careful if you're just trying to memorize things, right? So, but in that light, what I mean is I'm going to give you some definitions. I don't need you guys to memorize the definitions. I need you guys to be familiar with them when we apply them later on. You say, oh yeah, that's what that meant, and these are kind of things that go with it, okay? So don't worry about memorizing definitions. But, now that I say that, here's some definitions, okay. So, at the beginning of it, right, we're working through chemistry, which is but a science of things, right? And we could probably sit here and talk about the scientific theory, and you guys have probably already heard this all at some point, right? We develop a hypothesis, and we work through all the different aspects to get to the end, and we pat ourselves on the back, and then we call ourselves scientists, right? You guys are probably familiar with that side of it, right? Now, there's two parts of general chemistry, okay? Now, this is not something that is, I guess, explicitly shown here, but if you take general chemistry at a different university, sometimes they call it qualitative general chemistry and quantitative general chemistry. And it just refers to the different chapters that are being taught in the different sections, okay? So a qualitative general chemistry or qualitative data is just data that doesn't have numbers with it, okay? There's no numerical information. And so these are conceptual things, right? might be asking you to understand why certain molecules have a shape to them. There's no numbers that go with that, right? But there's an understanding that comes with looking at the shape of this. So the qualitative data, okay? Quantitative data, just kind of as the name implies, it deals with quantities, right? And there we have data that contains numbers with it, right? There are 40 of you in this room, right? That's data that we can do something with, right? So when we're talking about qualitative versus quantitative, we're just saying, hey, right, there's different aspects of the data that we have to deal with, okay? So to go back to this idea about the different types of Gen Chem, right? The first semester is a little bit more qualitative. I'm not saying we're not going to see numbers, but I'm saying if we put a giant umbrella term over it, it's more of the qualitative side of general chemistry, okay? So a little bit more conceptual. The second semester of Gen Chem, we're going to deal a lot with numbers, okay? Now something that you guys will see as I go along, I'm always going to be pointing to different chemistry classes when we deal with the topics in here. Why is that? Well, I want to scare you guys, right? Like, I have to remember all this? Well, yeah, but remember what I said about chemistry. Chemistry, by its nature, builds upon itself, okay? We are going to come back, and I'm going to talk to you guys about qualitative and quantitative at the end of Gen Chem 2, when you guys finish that class, okay? We're still going to be dealing with these things, okay? And all the other definitions are going to come into it here. So you'll see me kind of pointing to different parts of of this semester and of different semesters for chemistry also, okay? You guys with me now? Qualitative, quantitative, got it? Okay. So what is chemistry then? And I could ask you guys, okay, what's your definition of it and all these kind of things, and those typical types of conversation starters there. Well, let's see, the book says it's the science of matter and the transformations it can undergo. Okay, that's a fair enough definition, right? We're going to learn about things and then we're going to react to those things. That sounds fun, right? There's probably not too many people in here that don't like lighting things on fire. I know that sounds kind of, like a pyromaniac or something, right? Right? But we're going to learn about what happens when you light something on fire. Okay? What happens to the candle as it burns? We can assess the candle burning qualitatively, right? We could see how much carbon dioxide is produced. We could measure that, and that would be a quantitative data that we can get out of it. And both ends of that can tell us something about the reaction that's happening. You guys following along with this, right? In your mind, you guys have all seen a candle burn, and slowly it disappears, right? The wax goes away. That's a qualitative observation, right? Where does the wax go? Any thoughts? Yeah.
Heat.
Okay, so there's heat that's involved, right? So we got the flame in there. What does the heat do? Where does it come from? You guys ever thought about that? What makes up fire? Where does the candle disappear to? Oh, I'm sorry, yeah, what's up?
It transforms into the candle, the elements break down because of the heat, and
Mhm.
then it transforms into, I don't know what,
Okay.
but it does.
So the wax, the waxy thing there slowly breaks down into something else, right? Using heat to make this reaction happen. Well, what do we call a reaction that breaks things down with heat? I'll give you a hint, your cars do it, right?
Combustion.
Combustion reaction, right? So what's the difference between a combustion reaction in your car and a candle burning? The answer is not too much, right? Do they both produce energy? Is fire hot? Yes, okay, and not all of you guys nodded, I'm worried here. Right, write that down if you don't remember, right? Fire hot, okay? Right? Right? But we have a combustion reaction, right? In both cases, energy is given off, but we have to start the reaction, right? Fortunately, candles just don't spontaneously turn themselves on. That'd be worrisome, right? And so we're going to learn about why do we need to add a spark to get things going, okay? We're going to learn about what exactly the candle turns into. We're going to measure how much that is. The volume of CO2, or the amount of CO2 that gets produced from that combustion, okay? So these are the kind of things that we're talking about with transformations that they undergo. You guys are going to be able to predict the reactions. And then you can impress your friend by predicting what happens with a candle. Thank you. All right. Like, wait a minute, my friend won't be predicting. All right. I guess here at the bottom, that's kind of the important question. You know, one of the challenges is, why are you guys here, right? Now your answer might be, well, Dr. H, I gotta just do this to get through and get on to med school, or I gotta do this to get on to graduate school, or I just gotta graduate, please, 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 right? Okay? Whatever it might be, that's the answer that you guys have to have. Because why? Well, this is, you know, I'm not gonna lie to you, I'm not saying this is an easy class, okay? And so there's gonna be times where you're struggling through this, and you're like, I really don't wanna study anymore, this stuff is tough, I just don't understand it, I don't get it. I don't want to deal with it, I don't want to look at it. But you have to remember why you're here, okay? And hopefully your answer isn't just to, you know, check this off the list. I promise there's not a lot of majors where chemistry isn't important, right? It is one of these fundamental sciences, just like physics and biology and these kind of things. That's why we have it for you guys as part of your classes, right? You kind of build a lot of things off of this. And for those of you guys who are going on to med school or graduate school and this stuff, then I probably don't have to convince you too much that this is pretty important. Okay? How many of you guys are thinking about med school though? Quite a few of you guys. You know what one of the first classes you guys take in med school is? It's biochemistry. Okay? You know what biochemistry is? A little bit of bio, a whole lot of chemistry. Got it? So, are you going to see this stuff in biochemistry? You bet. Okay? Especially the stuff that we see in the second semester, kinetics and equilibrium. Okay? So we're going to be covering a lot of that stuff now. So, good news is you guys are saving money. Because if you're studying for Gen Chem, guess what you're also studying for? Med school. Got it? There you go. Okay. Thank you. I appreciate that. All right. So, qualitative versus quantitative statements. So what are the definitions? Here's some very, very, very tricky questions for you guys. So think about this stuff a little bit, see if we can get the pattern here, or see if we can get the definitions down, right? A compound is lumpy and yellow. What in the world, what information do we get out of that? Qualitative, right? It tells us about the nature of the compound, right? It's yellow, it's lumpy, it's a compound. What else does it tell us, though? Something that's a little bit more, let's say, hidden behind the fact here. Got to think about this in the chemistry world, though. So let's say I've got something in my hand that's lumpy and yellow, okay? I went to the cafeteria and it's lumpy. No, I'm just kidding. I don't know what it is. No, I'm just kidding. So think about this. If I'm looking at something and it's lumpy and yellow, in the chemistry world, that gives us some other information, such as it's a solid at room temperature, right? This is a solid at room temperature, right? It's lumpy, that means it's got shape to it, right? So we know it has to be a solid, right? So this is something that we have to start to pay attention to also. What information is given to us in the statements that we have, right? Now I'm trying to draw you guys' attention to problem-solving skills, reading comprehension, right? You guys all took the SATs or ACTs, these kind of things, right? Is reading comprehension still part of that?
Yeah.
Is it? Okay, right? So remember, they ask you, they make you read, for me, it was way too much, and they're like, hey, do you remember everything about this paragraph you had 2 minutes to read? No, right? But this is gonna be something that's important here, right? Reading and getting information about what I tell you in a problem, okay? So I'm really gonna ask you guys to pay attention to what's stated in that. So does that make sense? This also tells us that it's a solid, right? I made 24.2 grams of a snowy white material. What information do I have there? Right, I have both of them, right? Qualitative, quantitative. Okay, I've got how much I made, grams of things. That's a measurement of mass. We're going to talk about the SI units for how we measure things. Okay, it's white. It gives us some qualitative information. It tells us it's snowy. I don't know if, depending on what part of Florida, maybe I think we've all at least seen snow on TV, right? So, okay, but what else does it tell us? It's a snowy white material that we can gather the mass of, so we can make an assumption about its state also, right? It probably is going to be a solid also, right? And that will give us information as we move along into different parts of this semester, okay? I've got a lovely bunch of coconuts. That's just there because I'm done. Okay. So coconuts are a solid. That's important. Okay, no, I'm just kidding. Okay. I've got 12 liters of a gas, or excuse me, the volume of the gas is 12 liters. Okay. There we have some explicit information. We know how much we have in volume. It tells us it's a gas. It tells us about the state of things also. Right. Why do I keep focusing on the state here? Well, as we'll learn in chapter 10, I believe it's chapter 10. We're going to deal with gas laws. Guess what gas laws deal with? The laws of gases. Okay? So if I tell you I have a gas, guess what you have to use? Gas laws. If you have a solid, guess what you don't use? Gas laws. Got it? You don't use them until you have to. Make sense? Good. Okay. I'll confuse you guys later. Don't worry. There's plenty. The compound is impure, right? So here we have a qualitative statement. We made something in the lab. I didn't follow the directions properly, and we made something that's impure. Oh no, okay? So, but you guys get the point, right? Quantitative and qualitative, pretty straightforward, right? Okay, so now we got identifying some matter, right? So we got a couple of definitions here. A physical substance, something tangible. So that's what matter is, right? So at the top there, we got matter. Let's see, what color do we feel like today? Green? Nope. Let's try this one more time. There we go. All right. Matter, okay? A physical substance. Well, that's pretty much everything in the universe, right? So most of the things that we're dealing with, we consider it matter, right? A type of matter that has the same properties and composition throughout the sample. So that's our substance. Okay. And down here, we have compound. Okay. By the way, if you guys can't read my handwriting, just let me know, please. So matter, substance, and a compound is a substance comprised of two or more different elements. Now, colloquially, we kind of interchange all these, right? Matter, substance, compounds, they kind of all mean the same things, right? But you see how one of these kind of builds upon the other. There are specific definitions for each one of these, okay? So technically speaking, right, there is a difference between a substance and a compound, right? They don't have to be the same thing, okay? You guys with me on that? So just be careful. All I'm saying is there are different definitions for these, but again, I'm not going to sit here and make you guys write an essay on what the differences are for these things, right? I'm trying to get you guys familiar with some of the definitions of things behind the scenes, right? Sound good? people writing things down, so we're doing it here. What time's this class over? 11:50. You guys are always so honest. You're like, nope, 11:20, Dr. Age. Oh, okay, that's time to go. 11:50, okay. So, when let me scroll back here for just a second here, right? So if you're taking a look at substance, right? So it's matter that has the same properties and compositions throughout. So let's talk a little bit about properties here, okay? So I think this is something you guys are least familiar with. Examples of physical properties, right? So what do we mean by physical properties? So anything that can be measured without changing the composition of a substance, okay? So anything that can be measured without changing the composition of a substance. So what do we think? I guess I could say, in a way, measured or observed, right? Without changing the composition of a substance. What are some physical properties? Yeah.
It's state.
Right? Is it a solid, liquid, or gas, right? We can observe it, right? The state that it is in, okay? What else? The color, right? And you guys can see what color shirt you're wearing, what color the walls are, that kind of thing. What else?
Size.
The size of something, right? Can we measure something? Well, this is 6.5 inches, right? That's something you can do. Does that change the composition of it in any way? No, right? What else? So we got color, we got size, we got the state. What else?
Temperature.
Temperature. That's a really important one. Do you think you guys are going to be measuring some temperatures in labs this semester? Absolutely. Do you change anything by measuring the temperature? No, right? So temperature is a really important one. What else? Yeah.
It's a shape.
It's shape, very good, right? You guys have a bunch of notebooks in front of you. Do they have a shape? Did you guys observe that? Did you change anything by doing it? Well, in philosophy, right, you might, right? You'll make that argument, right? Am I really observing this, right? But that's not what we're talking about here, okay? So looking at the shape of something. At the bottom there, right, my field of expertise is something known as crystallography. So what I do is I look at like tiny, tiny crystals of things. And it can get us the structure of the molecules that are part of those crystals, okay? Have any of you guys heard of crystallography before? It's really important. How many of you guys have heard of Watson and Crick before? Anybody? Do you remember what they're famous for?
DNA.
Right, so Watson and Crick were the scientists who unraveled the structure of DNA, along with Rosalind Franklin was her name. She was a graduate student. And the way that they finally figured out this double helix structure of DNA is by using crystallography, okay? So I'll talk to you guys more about that if you go to some of the upper division chemistry classes, okay? But one of the important things in crystallography or mineralogy, if you're interested in geology, is you look at the shape of the crystals, okay? It tells you a lot about what's going on inside that crystal itself, okay? Plus, you know why I like it? They're pretty, right? They have very pretty shapes to them, right? There's a lot of symmetry behind, snowflakes and other types of crystals, right? So very, very pretty structures when you kind of zoom in and down on things. So it's important to think about the shape of things, right? So let's see here. So I'm going to write temperature down. Let's see, you guys had color, right? Shape. That's important. So let's think here for just a second. What else can we measure about something, right? What else can we measure about something that's a physical property without changing it? Yeah.
The weight of something.
The weight of something, getting its mass, right? That's pretty important. You know why? That's why Publix splits the scales outside, right? You guys are getting some quantitative information as soon as you walk out the doors here, okay? So that's important. I'm not originally from Florida, so it's always kind of weird for me. Like why in the world would they put that out here, right? Now I'm just part of it, I guess. I just accept it. What else? Yeah.
Volume and density.
Volume and density, right? Those are two separate things, right? You can measure the density of something, that's gonna be important. What do we mean by density? Well, we'll talk about it in just a little bit, okay? But volume's important too. Well, you guys be measuring some volumes in lab this semester? Yep. Well, you guys be measuring densities in lab? Yep. Well, you guys be measuring masses and shapes and colors and temperatures? Yep, right? All those kind of things in there. Do you have something or? Oh, sorry, what's your? You want me to call on you anyway to put you on the spot? No, okay, all right. Okay. So let me just add a couple of things here. These are going to be important, we'll talk about them a lot. Melting points, boiling points, okay? Pressure. And we could sit here and we could keep listing things out. In fact, if you go to Wikipedia, I think if you type in like physical properties, I think it's a list of like 57 different things, right? So I need you guys to memorize that by Wednesday, is that okay?
No.
No, of course not, that's useless information. But Dr. H, I like to memorize things, I know, right? But I don't need you guys to memorize these things, I need you guys to understand. And then we're going to figure out how to calculate some of these, okay? We're gonna talk about how to calculate pressure. Okay? We're going to talk about how to calculate boiling point and melting point and how to calculate shape. Thank you, right? It's a square, all right, okay? You guys with me on this? We're going to learn about all these different things as we go through, right? So we understand that we're going to be dealing with physical properties in this case, okay? All right, on the other end of things, and we have chemical properties, right? These become evident or they're observed when a substance is changed, reacted, or interacts with another substance, okay? I just have a couple of examples here for you guys. Zinc reacting with an acid, we're going to talk about what happens with that, okay? Sulfur burning in the air, that's just a combustion reaction, right? The rusting of iron, that's something called oxidation. So we're going to talk about reduction and oxidation, all these different kinds of things. So chemical properties, so these are actually going to be changing, right? Changing the properties. So we can look at things like toxicity, okay? Oxidation, right? Flammability. Make sure I got that spelled right. Heats of combustion. Let's see, chemical stability, so I'll just talk about stability here. Okay. Is it radioactive, right? Radioactivity. All these different kinds of things like that, okay? Again, we could go through and we could spend a lot of time talking about the different chemical properties that go along with this. Now, when we get to chapter 4, I believe, we're going to start to talk about different types of reactions. We're going to talk about what oxidation is and what reduction is, okay? We're going to learn why iron rusts, okay? Not only are we going to learn why iron rusts, we're also going to calculate how much energy it takes or gives off when that happens, okay? We're going to talk about heats of combustion quite a bit, especially when we get to the second semester of general chemistry, right? And unfortunately, just because of the way kind of, I guess, what's the word I'm looking for here? So there's a governing body of chemistry that kind of says, hey, if you guys are teaching general chemistry, you guys need to teach these topics. And the word for this is escaping me at the moment there. But anyway, they basically removed radioactivity as part of the list of things. So we're not really going to talk too much about that, unfortunately. But it used to be a topic that we talked about, nuclear chemistry. So it's going to be kind of taken out of this class. But I believe Chem 105 and 106, which we call the nursing chemistry, talks about radioactivity quite a bit, because in the medical field, you guys will be using radioactive materials quite a bit. Pretty important. So, but anyway, Alright. So now that we know everything that we need to know about physical and chemical properties, okay, now we have intensive and extensive properties, okay? So an intensive property is independent of the amount of substance that is present, okay? And extensive, dependent on the amount of substance present. Now, intensive and extensive properties can either be physical or chemical, okay? I'll give you guys a couple of examples there. So for instance, if we're dealing with the heat of combustion, okay, guess what the heat of combustion deals with? The energy that's involved with burning things, right? I think most of you guys have at least made a fire or been around a fire. If you throw more logs onto the fire, what happens? Does it get hotter? Flame gets bigger? What's that important thing I asked you guys to write down earlier? Fire hot, right? Okay? So bigger fire means bigger hot. This is on the exam, guys, okay? Multiple choice, true or false, right? Fire hot. What is it? Okay. So, if I have more fuel for something, if I'm burning more of something, I give off more energy, okay? And we're going to talk about the molar heat of enthalpy, okay? Doesn't that sound scary? Yes, okay? But don't worry, we're going to talk about that a little bit later, okay? But our molar heat of enthalpy just is going to deal with, well, if we can put 15 logs on the fire versus 5 logs on the fire, can we whittle that down into one number to predict how much energy per log, okay? You guys follow me on that one? We're gonna give it a kind of a standardization is what it is. So we'll talk about that as we go through a little bit later. Very important, okay? This? They were trying to steal it.
I know.
I stopped
This
it. Great.
looks like a sneaky class. Okay.
By the way, that's Dr. Tong. If you guys haven't met him before, he might be one of your,
I saw you
lab-
3 times in the calendar. I didn't get my face in the calendar once.
No, I'm specially
You
one.
must be. Keep an eye on that one.
Man, I was gonna hide it from him. Yeah, all right. Okay, so let's give a couple more definitions here about some other terms that we might be dealing with. So mixtures of substances. So there's two different types of mixtures that we deal with, homogeneous and heterogeneous, right? So 2 or more substances in the same phase, right? In the same phase, this is homogeneous. Let's see, did I get that spelled properly? Of course I did. Okay. So we have homogeneous and heterogeneous mixtures of things. Now, why is this going to be important? Well, kind of the first bullet point there under homogeneous is one of the key things to remember, okay? So 2 or more substances in the same phase, okay? So in the same phase. So first of all, what do we mean by a phase? Well, it's a phase of matter, right? Well, what are the phases of matter? All liquid gas, got it? You get what I'm saying? So we got multiple things that are in the same phase. Now, why is that going to be important? Well, you guys, or pretty much everybody in here, has their notebook or their laptop sitting on top of their desk, right? Is your notebook reacting with the desk? The answer is no, right? It's okay. Right? We sure hope not. Why are they not reacting? Could they react? Well, the answer is yeah, right? They could. Okay. Why are they not reacting? Well, they're not in the same phase, right? Okay, well, let's think about this here, okay? We've got air in this room. Is there 100% oxygen in here? No, right? What do we have in here? Well, we've got some nitrogen, We've got some oxygen, we've got some water vapor up here at the front. I'm talking a lot, whole bunch of hot air, right? Right? There's a bunch of different stuff, but are all the gases in this room in the same phase? Yes, right? You guys can't see a separation of different gases. Oh, well, at the bottom there's oxygen, at the top there's nitrogen, right? That's not happening. They're all in the same phase. It's a homogeneous mixture in here. You guys with me on this? Now, why is that going to be important? When we get to chapter, I believe it's chapter 4, we're going to start to learn about reactions. For things to react, they have to be in the same phase, okay? If they're in separate phases, it really, really, really kind of slows things down. I'm not saying they can never react, okay? But in terms of practical reactivity, okay, and within a reasonable time scale, right, they're really not going to do anything, okay? Let me simplify this a little bit. If you want to react things, you have to dissolve them into a solvent and have them mix around. So whenever you guys are going to be doing some reactions in lab, pretty much one of the first steps you guys are going to do is going to dissolve them into water or some other kind of solvent to get things into the same phase, okay? And then we can mix these things around, and then they can bump into each other, and then reactions happen. Got it? So we're going to be dealing with homogeneous versus heterogeneous mixtures, okay? I think I have some. All right, so what do we got? We got blood, we got air, we got apples, oil and vinegar dressing, milk, filtered ocean water, and we got some soda. So what do we have? When you zoom in on some blood, is it a mixture that's all in the same phase? I don't know, right? You know, are your cells dissolved in the water of your blood? Not really, right? So we do have some separate phases in there. So, have any of you guys ever donated plasma before? Right? So, it's a weird thing. I've only done it once. Right? So, they basically, you know, you go and they put the thing in your arm and they, you know, they bleed you and they give you a lollipop, you know, this kind of thing, right? And then they sit there and they centrifuge your blood down, right? And they separate, right, your red blood cells from the rest of the plasma that your blood is, right? And then they put part of it back into you, right? They only want a certain part of this, right? Sorry. Warnings, right? But they're separating the different parts of this, okay? So we have some red blood cells and proteins. You have some carbon dioxide that's dissolved in there. You have all these different things that are dissolved in your blood, okay? This is your second important thing. Is blood important? Yeah, okay, so next to fire hot, blood good, okay? Got it? So we have a heterogeneous mixture of this here, right? But we might not be able to see it until we zoom in on it, right? That's one of these tricky parts of it, you know? Air, well, we talked about that. We have air in this room, we have a lot of different things in it, but if we centrifuge this all down, it's still gonna be one mixture here, right? There's no way we can separate these things out unless we do some other science with it, right? Is an apple homogeneous? Does it have the same phase for everything that's in there? No, we've got the skin on the outside, then we have the flesh of it, we've got the seeds on the inside, right? We've got the leaves there, right? Maybe if we threw that all into a blender and mixed it all up really, really, really well, right, then it might all get into one phase, right? But that's changing something with it, right? We're adding energy into that system, right? You guys following me on this one here, right? We're blending things up, adding energy into it, okay? And I think you guys can kind of figure out the rest here, like oil and vinegar dressing, right? You guys have seen the Italian dressing sitting on the supermarket shelves, right? You see it sitting there, it separates out into the oil on the top and the water on the bottom, right? Or excuse me, the vinegar on the bottom, right?
Yes.
Now what does that tell you? Let's think here for just a minute. So we know that oil floats on top of water, right? What information does that tell us? Maybe some physical properties that we talked about.
Water's denser.
Water's more dense, right? So these are some of these observations to start to pay attention to, right? So what does it tell us if one thing's floating on top of the other, okay? Density is extremely important. We'll talk about this a little bit, okay? And we got milk and filtered ocean water and soda and all these kind of things, okay? Now, we're gonna bring this information into our reactions, and it's gonna be very important that you specify the phase of whatever it is that we're reacting. Is it aqueous? Is it solid? Is it liquid? Is it gas, okay? So these are the basically the 4 phases that we're going to deal with, okay? And we'll talk about what that means and how to deal with them when we get there, okay? All right. One of the most important things to start to think about. So kinetic molecular theory, okay. So what in the world are we talking about here? Okay, so let's break down a word, okay? So we have kinetic molecular. Well, what do you guys think of when we're dealing with kinetic? Where have you guys heard that, or what have you done with it, or where have you seen it? Kinetic energy, right? So in physics, so what is kinetic energy?
Energy in motion.
The energy of motion, right? Okay. Do you think kinetic means anything different here? Probably not, right? So we're dealing with the motion of things. Well, the motion of what? Molecules. Okay, do you guys know what a molecule is? Well, yeah, right? So we're just dealing with how molecules are moving, okay? So if you haven't picked up on it, I like to move around a lot. Why is that? I hate standing still, right? I got them antsy. I've got too much energy, right? You guys are kind of sitting down there and sitting still, okay? So molecules are the same way. Certain molecules move around a lot. They're zipping around, they're bouncing, they're bending, they're stretching, they're flexing, they're moving all these different ways, okay? And we can measure that. We can measure, and we can actually observe, okay, the different modes that molecules are bending and stretching in. And if you guys take organic chemistry, we'll talk about that, okay? Something that's important in forensic chemistry and forensic science and all these kind of things too, right? So we're just going to be dealing with how things are moving. Okay, so when we're dealing with this, okay, we're going to be relating the motion of molecules to their phase, okay, to their state, solid, liquid, or gas, okay? This is going to be important. So we're dealing with a solid, okay, by definition we have closely packed particles in regular arrays, okay? A couple of important things here. They're closely packed, okay? That's going to be extremely important. In chapter 7, yeah, I believe it's chapter 7 or 8, we're going to talk about how molecules talk to each other, okay? And just like you guys in this room, if I ask you to lean over to your neighbor, right, and ask them what their favorite kind of cheese is, okay, you guys could accomplish that, right? Do you know what his favorite cheese is? What's your favorite cheese? Pepper jack. Okay, now we know. Okay? But if I ask you to go talk to the young lady all the way in the back there, right? That would be slightly more difficult to accomplish. Well, why is that? Well, you guys are closer together, right? You guys are further apart. So molecules behave the same way. The closer they are together, the more they can communicate. But they have different ways of communicating, okay? Twitter, email, okay. We're going to talk about these different ways, okay? So it's important to recognize the closely packed part of this, okay? Fixed locations. Well, you guys kind of figured this out too. Is your desk moving anywhere at the moment? Nope, right? But are the gases in this room moving around? Absolutely, okay? That's going to be important also. Rigid materials, small fixed volume. We'll talk a little bit about the volume of solids and these kind of things when we get into a little bit of the introduction of unit cells and things like that. External shape often reflects the inner structure. Yeah, maybe. I might argue a little bit with that, but that seems fair enough. Okay? So, are the molecules in your desk moving around a lot? The answer is, it depends, right? What do you mean it depends? Well, if you asked a physicist, they would say yes, they are moving around a lot, okay? If you ask a chemist, they'll say probably no. So as with some sciences, things are relative, okay? Well, how do we know, how are we going to measure, for the beginning part of this class at least, how much these molecules are moving around? Well, we're going to take things called temperatures, okay? So kinetic energy, right, is just the motion of these molecules, and we're going to measure that through temperature, okay? So if we add more energy into a system, if we add heat energy into a system, that heat energy has to go somewhere. Where's it going to go? Into the molecules. And what's going to happen to those molecules? They're going to move around more. Makes sense, right? If I came in here and I gave you guys all a bag full of sugar and said, go ahead and eat it, okay, are you guys going to start moving around more? Yeah, right? Am I giving you guys energy? Well, maybe not. What about Jolly Ranchers? Is that better? You know, imagine eating a bag of sugar, right? Right? If I give you guys energy, you guys are going to move around more. That's why you guys drink coffee in the morning or tea, right? Get some caffeine, get you guys going. Same thing with molecules here, okay? If we add energy into something, they're going to move around more. Did you guys already know this? Sure, right? What happens when you boil water? It goes from water as a liquid into water as a gas. Do gases move around more? Yeah, right? So you guys got it. Okay, move to the liquid. Closely, oh, let me back up here for just a second, real quick, just to make a kind of another trivia point, I guess. You guys are going to dominate a trivia from that one, at least the chemistry side of things. Okay, rigid, no, where was it? Where was it? Okay, so closely packed, often regular arrays. Okay, so this is going to depend a little bit. Okay, so we have glass. Is glass a solid? Yeah, yeah, but it doesn't actually have a regular array long term, okay? So there are things called amorphous solids. You guys heard that term before? Right? Amorphous solid is what glass is and certain other properties. In fact, for those of you guys who are interested in polymers, okay, or liquid crystal materials, right, display technologies, knowing about these amorphous solids is pretty important, okay? An amorphous solid has local order, but not long-range order, as opposed to your desk, which has long-range order the whole way, okay? So even within solids, there is some variations, and those variations give important properties, okay? So liquid crystals kind of work off of this local versus long-range order idea here, okay? But there we go, there's your tribute. All right, liquids, closely spaced, okay? Very similar to solids in that sense. Something we didn't talk about with solids, but you guys can work through a visual experiment here. Can you guys compress your desk? Even if you, right, even if you work out every day, right, can you press your desk down and squish it? Not easily, right? Why is that? Well, there's not a lot of free volume in there, right? That's the whole idea. So can you compress a liquid? A little bit easier, right? But still the same idea. There's not a lot of free space inside of liquids, okay? Slightly larger fixed volume than a solid, more randomly arranged than a solid, okay? Liquids are kind of tumbling and moving all over the place, okay? But you guys knew that too, right? Because if you have a pitcher of water and you tip it, what's going to happen? It's going to pour out. Why is that? Well, the molecules are flowing over each other, right? These molecules are moving around. If you take your desk and tip it over, what's going to happen? Your neighbor gets mad because you knocked their computer off, right? But the desk isn't going to do anything, okay? It's not going to, these molecules aren't going to flow over each other, okay? This is going to be important here. Constant collisions with the neighbors, okay? We're going to talk about how reactions happen, okay? And I'm going to relate it to a car accident. Reactions happen when molecules come at the right time, at the right speed, with the right energy, at the right angle, with the right orbitals, and they hit each other, okay? There has to be some, for the moment, we'll say, physical contact between two molecules, between two atoms for a reaction to happen. So it's important that there are collisions, okay? That's what's going to start a reaction, at least for us to happen. Gas, continuous rapid motion, particles widely spaced, travel large distances before colliding, no fixed volume or shape. What's important about gases is that we're going to work with ideal gas law, and that's going to kind of restrict our math and our ideas that we kind of share with that, I guess. But one of these important things is that they're widely spaced, so there's not as many collisions as we see with a liquid. Okay? Sound good? Kinetic molecular theory, things moving around, solid, liquid, gases, things collide, okay? Uniform distribution of molecules versus non-uniform distribution of molecules, all these kind of ideas. I think that'll be a good place to stop for today. We'll pick this up on Wednesday, and keep moving our way through chapter 1.